Now that we've established the identity of our building blocks, we can move on to our next topic, which is to understand their behavior. And we're going to begin then by looking at a very interesting experiment, something known as the photoelectric effect. And the interesting thing about this experiment is that what it's doing is it's looking how electromagnetic behavior, right, namely photons, meaning light, how electromagnetic influences actually affect electrons. And this experiment, a classic experiment, was carried out by Leonard in 1899. So we're really talking only just 2 years after the J.J. Thomson experiment. And it's another one of these cathode ray tube-like experiments. So I'm going to have a vacuum chamber. It's going to look something like this. This is a schematic of my vacuum chamber. And once again, it's going to have a cathode in here that I will attach to the negative side of a voltage source. And there's also going to be an anode. And I'm going to complete this circuit, and I'm going to insert one extra device now. I'm going to insert an ammeter in here so that I can measure the amount of current I flowing through my circuit. Now, so that we can study how electrons interact with light, I'm actually going to shine some light down onto my cathode. And this is going to be light. And I'm going to describe the light with two variables, the brightness, which I will call B, and the frequency of the light, which we will call nu. Now, the interesting thing is that unlike the cathode ray tube experiment of Thomson, where we cranked up a very negative voltage here to push the negative charges out of our atoms, what we can do now is stay at relatively low voltages, but shine light onto those electrons and deliver energy to them through that light. And sure enough, if you do that, particularly with ultraviolet light, electrons will begin to come off. And they will come off in a variety of different directions. And as they come off with different amounts of kinetic energy. And sometimes they've got energy and they're traveling in just the right direction, and they actually will land on my anode and then complete my circuit so that then I can actually count exactly how many electrons per unit time make it from my cathode to my anode by doing a very simple electrical measurement, just measuring that current I. So it's really a beautifully and ingeniously designed experiment. Now, the results that we get from this are just as interesting. So here's how we would plot the results. So here I'm going to be plotting for you the current that I get as a function of the voltage V. And for now, we're just going to keep the brightness of the light and the frequency of the light fixed, and just simply change this voltage and measure the current. Now at 0 voltage, as I was just saying, when there's no voltage applied, still the light will eject electrons, and some of those electrons make it over to my anode, and I actually do measure some amount of current. Now, as I go to more positive voltages, I would be making my anode positive. That makes it more attractive to the electrons. So now, some of these electrons, which previously would just be running into the side of my chamber and not participating in my circuit, I can begin to bend their trajectories and pull them in. And so as I go to more positive voltages, making this attractive to the electrons, I can pick up more electrons, and my current will actually begin to increase. And that will go on for a while, but eventually I will saturate out at some maximum saturation current. And the saturation occurs because at a certain point, I've made this positive enough that any electron that manages to make it out of the cathode is going to be sucked up by this very strongly positive anode, and I'm going to be then measuring all of the electrons that come out. Now, what's interesting about this is that the shape of this curve and how it approaches that saturation current gives me all kinds of information, for example, about the direction and kinetic energies of these electrons, right? Because the reason why I start to pick up more and more here is that I can bend more and more of them off of their trajectories and pull them into that anode. So there's all kinds of information here about the distribution of angles and energies of my electrons. Another interesting thing is that I can ask, well, what will happen if I go to negative voltages? As I go to negative voltages, I'm going to be charging up now the anode as negative. That makes it repulsive to the electrons. And so I'm going to be bending my electrons, I'm going to be then bending my electrons then away from my anode, and I'm going to be picking up fewer and fewer of them. But still some of them, which come off in a good straight across direction with a good amount of kinetic energy, can still make it. So as I go to more and more negative voltages, what I see is my current begins to drop. And I do reach a certain point where the current actually stops completely. And that voltage is called the stopping potential. I will call it Vs, but just to emphasize that it's negative, I will write it as its absolute value there with a negative sign. Now this is interesting because there is a certain critical stopping potential. When I go this amount or more negative, I get 0 electrons. And what that is telling me is that there is a certain potential or potential energy between these two plates that I can apply that stops all of the electrons. So that tells me there is a certain sort of maximum energy electron that is generated in my process. And this is giving me a measure of its kinetic energy that it tries to use to overcome my potential, but it just can't. Now, Leonard then continued this series of experiments, and he made a very interesting observation in about, it was actually 1902. And here what he began to do was he began to study this phenomena and how the current depends not only on the voltage, but on the light itself. So he began playing with the light. He began adjusting the brightness, the intensity of the light, and also, of course, the frequency. And here's what he found. So he found something very interesting. He found that if he exactly doubled the brightness, say, so this would be a curve, say, at brightness 1, the first brightness. If he exactly doubled the brightness, what he would find at 0 voltage would be exactly double the amount of current. But what was really fascinating about this is that when he does that, he doubles the amount at 0 current, but it's not just at 0 current. The entire curve is simply just doubled or multiplied by 2. So this would be at the second brightness. But it's an exact perfect copy. And why that is important is because it tells us something about the energy distribution of our electrons. Remember, right, that the shape of this curve is telling you something about the angles and energies with which these electrons emerge from my surface. When I double the brightness, evidently I'm getting twice as many electrons, but the shape being exactly the same tells me they're coming out with exactly the same energy distribution. But this is very mysterious, right? Because the brightness tells you how much energy I'm pumping down. So I'm pumping down more energy per unit time, but still somehow I get the exact same energy distribution in those electrons. So, what really is that about? So, just to summarize his result, if you want to be mathematical about it, it's doing something called a scaling law. And what that scaling law is doing is it tells us how we can relate the current, as a function of voltage. But now I'm not going to be measuring that current at a simple voltage V. What I'm going to be doing is I'm going to actually change the brightness. So I multiply it by some number alpha. In my example, it was double. But whatever it is, you multiply the brightness by a certain amount, and then you're studying what happens at a fixed frequency. And what you get back then is exactly twice, or whatever number alpha you were using, the current that you started with in your original experiment. And this somehow tells us that the energy distribution of the electrons is unchanged. So we just get more electrons if we increase the brightness, but the same energy distribution. Now that's quite mysterious, because what we are doing is getting that with more energy that we're pumping in. Now let's try let's go down to now and think a little bit more about this energy issue. There's another interesting fact that was discovered sometime later. Later they observed something very interesting, is that the emission of these electrons, as they are pulled out of the surface, is actually almost instantaneous. It basically happens at the speed of light. I mean, they don't travel at the speed of light, but they start coming out as soon as the light hits the surface. And that's very, very mysterious also. The reason that is so mysterious is that if you think about the amount of energy that you are delivering in this light, you can figure out exactly how much light is hitting a given atom. And so you can figure out how long it would take that atom to build up enough energy so that its emitted electron would have this kinetic energy that we know they have because we know that stopping potential. And it turns out that it actually would take a lot longer to build up that energy than the actual time we see the electrons, how quickly the electrons are coming out. So we know somehow the energy is being delivered instantaneously, very, very quickly. That's a big mystery also. Now, he also observed later on, well, the other observation was that if you do change the frequency of the light nu, right, then in fact you do change the shape. Then the shape actually does change. And that does affect the energy distribution of the electrons. So somehow energy has nothing to do with the energy we're pumping in, but the energy the electrons pick up has something to do with the frequency of the light. Now, the person who did actually the definitive experiment on this, on the shape change, was Millikan. And Millikan, this is our famous Millikan, he did these measurements in 1915. And this actually was so important that this was the second half of his Nobel Prize. And what he did to think about that shape change is he focused in particular on this stopping potential. And he made a detailed study of how that stopping potential depends upon the frequency of the light. And in particular, the way he plotted it is he plotted it, here I'll write I'll use the positive version of the number, the absolute value of that stopping potential, multiplied by the electronic charge. So what we know this really is telling us, if you think about it, is this is telling us the kinetic energy of the maximum energy electron that is emitted. Because this shows you how much potential energy we need to put between them in order to stop all of the electrons. So when he made this plot, he found a very interesting result, which should make any physicist's hair stand on end. So what he found was he gets a perfect straight line. And the way that this line works is it begins at a certain frequency nu naught, so that below that frequency, in fact, you don't need any stopping potential. The stopping potential drops to zero. There's actually a certain minimum frequency that just doesn't give the electrons enough energy to escape. And this energy, or this frequency, I should say, perhaps not surprisingly, really does depend on the material. So this is material dependent. But the interesting thing is the rest of the curve. It's a beautiful, perfect straight line that has a given slope. And this slope is a constant slope, right, because it's a straight line. But not only is it constant slope, it's a constant slope with a universal value. What that means is it doesn't matter what material at all that we are using. You get exactly the same slope, even if you're using some kind of a compound, or you change from platinum to copper, or any type of electrode that might interest you, right? You always get exactly the same slope. So that slope is material independent. And these then represent a set of very mysterious experimental findings that then demand an explanation.